Hello, this is your walk and talk for, let's try this again, Friday, August 9th, 8:51 p.m. And we're doing our second walk around. And today what we're going to do is two things. We're going to test how jostly this camera is, how good the voice recording is, and we're going to talk about what to do with the clock because I owe my dad a clock. So, as far as what we're going to do about the clock. I got to looking back at the clock boards that we have, and the bottom board, it has the everything runs on 3.3 volts, and the microcontroller runs on 3.3 volts, and there's a step-up converter to go from that to 5 volts to control the shift registers, and the outputs of the shift registers go through a set of resistors, which then go out to the lights and control the lights and blink all the lights, and everything's happy and good and cool. Which is all fine, except that now on the front board there is no interface between 3 volts and 5 volts. All the shift registers run on 5 volts, and there's no resistor between them and the power supply, and the LEDs. So what I'm thinking is that back in the distant past, last year when I designed these boards, that I had convinced myself that it was okay to run those shift registers on 5 volts, and that it would still get less than VF on the LEDs. So then I've made one of those front boards and stuffed all the green LEDs on it, which is all fine and good until if I were to find out that it was no good, I would burn up all 60 of those LEDs and whatever else I soldered on that board. Not what I want to do. So what I'm going to do instead, well, think about this two ways. There's the cautious way, there's the, we'll say, the NASA way, and that is that we will get a breadboard shift register, run it on 5 volts, run it with an ESP, run it with the Nano with the ESP output, so it's got 5 volts out, and we'll run that through one of our breadboard LEDs. It's hooked up, and we can measure what the actual voltage output is. And the thing is, I've got one of the surface mount shift registers already mounted on a surface mount to breadboard adapter. So I will happily go ahead and use that, and then feed it with 5 volts, control it with 3.5 volts and see what happens, and then run the supposedly 5 volt output through an LED and see what happens. And my suspicion is that what I decided before is that the internal resistance of the shift register output was high enough that it basically took the place of the resistors. It took the place of the resistors that the LED calculator says that you need. But I can verify that because I can get a 5 volt Arduino. In fact, that's the thing, is I've got a 5 volt Arduino that I can hook up, and it has 5 volt logic on it, so I can make sure that I'm driving the shift register right and all that good stuff. In fact, that's what I'm going to do, is run the whole thing on 5 volts. And it's got a A to D with 5 volts on it, so I can hook it up and actually measure the power consumption on it, and life will all be good and stuff. And see, that's the NASA way of doing it. And I know this because I was just watching a Curious Mark video where they had the NASA way of putting a old Apollo Universal S-band transponder onto a test bench. And they had a whole rack where they even had a drawer that they could put the whole transponder, the whole 30-pound transponder, into a drawer in the rack, plug it all in, and test it out, and test out all its inputs and test out all its outputs without actually hooking it to anything else that was supposed to be flight ready. So that if this one failed, it wouldn't contaminate any other flight ready hardware that it was attached to. So yeah, that's the NASA way to do it. The SpaceX way to do it is to consider that the board and the LEDs that I've attached to it are already expended. If it's wrong, then I'm going to have to respin the board anyway. And if it's wrong, and I find this out by burning out the LEDs, well, the LEDs were soldered to a bad board anyway. So the less courageous way of doing it is to solder on some shift registers and just run it. Just finish making a board with the front side shift registers and the back side interboard connectors, and just fly with it. And we could do that and it would be happy and good and cool if it worked. And I'm pretty sure now that thinking over what I did, I'm pretty sure that I did in fact do what I said, which is that I did work in the internal resistance of the shift register. And so, yeah, because those things, they're not really rated to deliver 24 amps or 24 milliamps and to source 20 milliamps and sink 20 milliamps. So what's going to happen is that there's some kind of internal resistance between 5 volts and the output, and which means that just because there's a internal resistance, the more current you draw more current by putting a lower load resistance on it. And the lower the load resistance is, the lower of an effect it has, the less voltage is dropped across it when you consider it in a voltage divider with the internal resistance of the output lead. And so, and what I'm going to do it the NASA way, I'm going to get one of my 5-volt Arduinos, put it on there, and do it all up properly. We use the ADCs as 5-volt voltmeters, so I can get a voltage and a power and get voltage and resistance and all this other good stuff and blah blah blah. And what I could really do is, okay, so 2 things that could be done. We could go by the spec sheet and believe it that it says that if it has X volts across it, then it has I milliamps through it. We believe the IV curve that's in the data sheet. And that's probably okay. I mean, you've got this data sheet, and then you've got things like the VF might be scarily out of, there's a scarily wide tolerance on that, wider than I have any reason to believe it's actually real. So I'm going to choose to believe the IV curve rather than the spec on VF, and say that if the LED has 3 volts across it, 1, it's safe because that's at or less than VF, and 2, whatever the IV curve says is what the voltage across it, or the current through it is. So I can do that, and I can measure the VF across it, because the input to the high rail of the shift register is going to be 5 volts. The low rail of the shift register is going to be 0 volts, and there's nothing we're going to do about that. So I'm just going to turn around right now. So all we will want to do is measure the voltage at the high end and low end of the diode. And so we'll be able to see that it is 3 volts or whatever it is. And we'll look at the IV curve and we'll say, okay, that's 20 milliamps. And then we'll say, well, if the high end of the diode is at 4 volts and the low end is at 1 volt, and V in is at 5 volts and V out is at 0 volts, then that means that it's 1 volt across the internal resistance of the high output and another volt across the low input resistance, the low output resistance of the low output. And then 1 volt, and we look at the IV curve and say that it's 20 milliamps. So E equals IR. R equals E over I. 1 volt divided by 50 milliamps. It's 1 volt times, so it's 20 ohms. 20 ohms on the high side, 20 ohms on the low side. And that just means that you put 5 volts across a resistor, or a diode that drops 3 volts, and then enough resistance to drop 2 volts, and there you go. Yeah, it eats all 5 volts and it draws the appropriate amount of current. So that's what I'm going to do. And I'm pretty sure it's going to work because, like I said, the shift register that I have is just an adapted normal shift register, surface mount shift register. And it's just going to work, and I'm going to control it right. And life will be good and everything will be fine. And I'll be able to show that, because it's this hardware that's annoying me. I put 60 yellow LEDs on a board, and 58 of them worked. And I put 60 red LEDs on the board, and 3 of them fell off, and 8 more of them don't work. And included in all of that, included in those 11 that don't work, are 10 in a row that don't work, which makes me really suspicious that I screwed up the bottom board, or the back board, and that I'm going to have to respin or green wire that. And I'm going to follow my internal rule of green wiring it before I respin the board. And that's going to be an interesting, fun challenge, because it could be software, or it could be a hardware green wire, which means I have to cut one of the 6 mil traces without cutting any of the other 6 mil traces, and then solder to one of the terminals of those 0402 resistor arrays. Not fun. I know that I've done it, but I also know that when I did it, it was 13 years ago, and I was much younger and had the temerity of youth, which is something I need to write an essay on. NASA had the temerity of youth when they did Apollo. In fact, I don't need to write the essay on it. The Phantom Tollbooth is the essay on it. Milo succeeded because he didn't know that he was trying the impossible. The Mathemagician and King Azaz the Unabridged, they knew that it was impossible, so they didn't try. And Milo didn't know it was impossible, so he was able to do it. And there's something to that. And the something to that is what I've said before. This is the part of the essay that I need to talk about, is that if you know something is impossible, if you have a contract to do something, and if it's not done, there will be consequences, and it turns out the thing is impossible, then it doesn't matter what you do to try and fulfill the contract, you will fail and default and pay whatever penalty clause is on the contract. And so, if anything you do will result in the same penalty, then doing nothing will also result in the same penalty. Therefore, you have no obligation to do an impossible task. So, there's a kitty cat. And this has been Con 3217 with today's Walk and Talk.